In this video, we're going to talk a little bit about linear modeling and specifically general linear modeling, with emphasis on the word general. When you first come across statistics, you're often bombarded with a seemingly overwhelming number of different sorts of tests and different sorts of model that exist. And you're often taught in a way that really emphasizes the difference between some of these methods when you're taught about t-tests and chi-square tests and analysis of variance and linear regression and logistic regression and multi-level modeling and so on and so on and so on. It can feel confusing and complicated to try to work out exactly what this all means and how this fits together and what methodology you might need to use for your particular use case for whatever research or data it is that you're trying to work with. But in reality, there's actually nowhere near this number of different methods and different tests. We have a family of models called a general linear model, which encompasses quite a lot of those introduction first class of statistics, even second class of statistics methods that you come across. They all are effectively exactly the same thing. And those sort of models are a subset of a slightly wider set of models, which are generalized linear models, which include a few more tweaks to the way in which that modeling framework works, but are really not that different from general linear models. And then there's one more step up from that, which goes to generalized linear mixed models, which again, it's a lot of the same common DNA as exist in generalized linear models. We just make a little bit more of a modification to the formulae. So there are more statistical methods beyond just these three categories of models, but you're covering a huge realm of those statistics that you are taught and you use to do all sorts of different things just by knowing three kinds of method, not by knowing 100 different kinds of method and being completely overwhelmed by all these different concepts and all these different terminologies. Let's break that down a little bit more, and perhaps you don't believe me, and I'll try and convince you. So when we're talking about a general linear model, what we mean is any model which can be simplified to a particular form, where we have a response variable that we'll generally call y. We have some combination of predictor variables that we will call x, with a capital X, because that will be a matrix with potentially more than one variable accounted for. And we have coefficients that we call beta applied to each of those x variables. And that's it. We also would have an error term on top of that, which is a little epsilon in the formula there. And a key part of the general linear model is the assumption that we make about that error term, because we assume that our error term roughly follows a normal distribution with a mean zero, and we estimate a parameter for the variance of that error term. Mathematically, that feels a little bit abstract. It starts to make a lot of sense, though, when you apply it to specific contexts. So let's look at what usually might come to mind when you hear the word linear model, because you probably have been taught in other statistics classes about linear regression. And that's where you consider a numeric variable as your response variable. So in this case, we've got data from Australia about various factors which may affect the yield of soybeans. So we're looking at our yield as our response variable on our y-axis, and we're comparing that against a predictor variable on our x-axis. In this case, this is the protein content of the soybeans, and trying to see how these two variables link. How much does the change in the protein content of a soybean affect the yield of the soybean? And we can do a nice scatter plot where we see some kind of relationship between the two. As our protein content of our soybean is increasing, the yield is decreasing. We don't see a particularly strong relationship. We can see there's lots of variability away from the line that I've drawn on the graph there, but there certainly looks like there is some relationship in this trend that I'm trying to assess here. And this breaks down to a straight line. And a straight line has an equation, which is something which you didn't learn in statistics, you probably learnt when you were about 14 or 15 in school, the concept of y equals a plus bx, or y equals mx plus c. And when we formulate it as a statistical model, we change around the notation a little bit, but it's still the same equation. We call it y equals beta naught plus beta 1 x, where beta naught is the same as the c if you learnt it as mx plus c, or the a if you learnt it as a plus bx, which is the intercept term for our straight line, and the beta 1 is the same as our m, or the same as our b, depending on which version of the equation you learnt, which is the slope of our line. And we can use any statistical software to calculate our linear regression model and to formulate this equation of a straight line to get us a linear regression. Our y equals beta x becomes yield equals 6.92 minus 0.13 times protein. In other words, if we look at our 6.92, this would tell us the intercept of the line. So if the protein content was equal to 0, what would we expect the yield of the soybean to be? And that's 6.92. And the 0.13 refers to, okay, as we increase the protein content by 1, what would we expect the change in the yield to be? So it will decrease by 0.13 units as we increase protein by 1 unit. And we also, associated with that, have this residual error term, which helps to explain the variability away from the line. And in the output here, you can see that mentioned under the residual standard error. So this is 0.702 is our residual standard error. So when we're formulating this error term, we're assuming that it is based on a normal distribution and it has that level of standard deviation in terms of how spread the points are away from the line. There's a lot of assumptions which come into how this model is formulated, how the parameters are calculated. This normality assumption is one of the assumptions, but perhaps not actually the most important assumption. I'll talk a little bit more about that towards the end of this video. But the way in which it's calculated goes through a set of algorithms known as ordinary least squares. And that set of algorithms is common to the general linear modeling framework. All of the models within that family use exactly the same underlying algorithm to determine the coefficients, the significance, the standard error, the variability, and so on. And that's why all of these different methods are actually functionally identical, even if they're being used for slightly different contexts and then having names applied on top of them. I won't go into too much detail about each different specific method, partly because, as I'm explaining, to me these are all the same method, but there's plenty of resources and additional videos to dive in more, particularly diving in more to a linear regression example, because that's quite a good starting point to understand all the different components which go into a general modeling framework through using linear regression as your jumping off point. So there should be some links below to other more detailed resources to go into the concept of linear regression in a bit more detail than I'm going to go into in this video today. Beyond our linear regression model, let's think of something else that we might have in this data set. And as well as the information about the protein content, I know in the soybeans I've got, they came from two different seasons. I collected them in 1970 and in 1971. I'm using quite an old data set here, as you can tell, to make my point. And I can do some exploratory summaries, and I can kind of see that it looks like generally my yields were a little bit higher in the second season than in the first season. And conventionally, if I'm looking at this setup, I've got, okay, exactly 2 years. I've got a numeric variable yield, so I should just do a two-sample t-test. This is the perfect setup for doing that as my analysis. And there's nothing wrong with that. If that is my specific question here, I can run it through my statistical analysis program. It will tell me that I have very, very strong evidence indeed. My p-value there of 2.2 e minus 10, so that's 9 zeros and then a 2 in terms of how small that p-value is. So we're pretty confident in rejecting our null hypothesis and saying that, yes, the yields in 1971 on average were higher than the yields in 1970. But that's all I can do from a two-sample t-test. I could feed the exact same data into a linear model. My linear model function in R, in this case, gives me a slightly different looking set of output to the t-test output in R. But when we start to look in a little bit more detail, we see a few things. We can see, okay, this 1.83 for the mean in 1970, that's in both sides of the page. So's the minus 6.49 for my test statistic for my t-test. Oh, so's the p-value, that's also the same. So's the number of degrees of freedom, that's also the same. Oh, and my confidence interval, look at that's also the same confidence interval. The one number that's not quite explicitly on both sides is the number for the mean in the second group. To get that, we'd need to add up two numbers on the right-hand side, so that the minus 0.183 and the minus 0.43 from the estimate column of my linear model. If we add those up, we get the final number from the t-test. But the first thing you might start to spot is there's still lots of numbers remaining on the linear model side of the page, which are not accounted for at all on the t-test side of the page. Because using a model rather than a hypothesis test gives us a lot more grounding for doing different sorts of things, for testing different hypotheses, or for making predictions, or for building a summary of the variability as well as building a summary of the difference in the means. So this is why, for me, I would personally never even do a t-test, even if I had a very simplistic situation where I just had one outcome variable and two groups. I would go straight to thinking how I can formulate this in terms of a general model. And if we start to break down how this fits into that formula of y equals beta 0 plus beta 1x, or y equals beta x in general, with the t-test, the formula is actually identical to the formula for a linear model. The only difference is how we consider what x refers to. So we still have a beta 0, we still have a beta 1, we still have an error term. The x in this case we consider as a binary variable rather than as a continuous variable. So as we increase our x by 1, which is the interpretation we make when we have a continuous x variable, this now becomes, okay, if the year is 1971, that x takes a 1. If the year is 1970, the x takes a 0. So that now provides the difference in the means between 1971 and 1970. Because we multiply it by 0 if it's 1970, we multiply it by 1 if it's 1971. And our intercept becomes the mean value of our first group, the one that's coded as 0 in our binary variable, which is why our 1.83 is the same as our mean value in 1970. And if we wanted to get our mean value in 1972, we would, or 1971, sorry, we would add up our 1.83 and our 0.43. And it's not just t-tests. So an analysis of variance is still a linear model. In fact, you could consider a t-test to be a subcategory of an analysis of variance, where you only had two groups rather than any number of groups. And you could consider an analysis of variance to be a subcategory of a linear model, where you happened to have a categorical variable rather than a numeric variable. And in this case, we have multiple coefficients. We don't just have beta 1x1. We have minus 1 from the number of total groups coefficients. So we still will have what we call a reference level, which will be the first group that we choose. By default, it will usually be the first group alphabetically, and that one will be zeros for all of our new x1, x2, x3 variables. And then the next group will take a 1 for x1, all the other groups will be a 0. The next group will take a 1 for x2, where all the other groups will be 0. And the final one will take a 1 for x3, where all the other groups will be 0. And that lets us estimate the difference between all the different combinations of the groups by having different parameters for each of the groups. I won't go into too much more detail for these examples. Like I say, there's plenty of additional resources to really dig into the specifics of these models. One of the things that surprises people as well is actually non-linear trends can still be linear models. So if we think of a curve which is slowly flattening off, we can make that with a general linear model by, rather than looking at the effect of x, looking at the effect of log x. And that produces a nice curve which will go up and then flatten off. Similarly, we could create a curve which goes in the other direction and increases exponentially by looking at the exponential of x. Or we could have two parameters and turn this into a quadratic curve and have something which goes up and then goes down again by having one term for x, one term for x squared. This still fits into that general linear modeling framework. And even to extend it further and further and further, if you squint hard enough, non-parametric tests are also general linear models, except we're looking at the rank transform of the variable that we're interested in. Chi-square tests, also general linear models. I've included on the screen some links to some really good resources which go into this topic in a bit more detail, just to fully convince you of how pretty much everything that you learn in your Introduction to Statistics class is actually just a general linear model wearing a slightly different hat. But why is it actually useful to think of it in these terms? So, as I kind of mentioned already, the modeling framework is a more flexible framework than a test framework or a hypothesis test framework. We specifically quantify the relationship. We build that equation which lets us make predictions. It lets us test hypotheses in different ways rather than just testing the hypothesis of, is there a difference, is there not a difference? We can start to build custom hypotheses to understand better how our model is constructed and how the effects of our variables link to our outcome. And it also provides us with that starting point to bring together multiple different variables. So if I think of the first two examples I gave, the protein content of the soybean and the year the data was collected, these don't exist in isolation. Each of those observations from 1970 has not just a yield associated with it, it also has a protein content associated with it. And it will be the same if we think about the location or the size or any of the other variables in our data. If we're trying to understand what links to the yield, we want to try to bring together all the data we have to make the best possible model to provide a summary of the yield. And thankfully, if we deal with more than one variable at a time and make a multiple regression model, you guessed it, this is still a general linear model. So I've plotted here the protein content and the year on the same plot. We're using different colors for the different years. And if we think of our general framework and our general formulae, now we have a y equals beta 0 plus a beta 1 times x1 plus a beta 2 times x2. And x1 will refer to our protein content, and this is a continuous variable. Beta 2 will refer to our year, which is the same binary variable that we considered before. When we start to have this equation which has more than one variable in it at a time, there is the additional extra caveat in how we interpret things, where when we're trying to assess the slope parameter here, so the 0.13 or minus 0.13 times protein, to understand what that means, we need to say that we hold everything else in the model constant. So for a 1 unit increase in protein, we expect the change of the yield to be decreasing by 0.13 units if we are considering a soybean collected in the same year. And similarly for the year component, the difference we expect is 0.72 units of yield if we are comparing two soybeans which have the same protein content. And that's a really important caveat to remember because it's something that people make some quite big mistakes in and make some quite fundamental errors where they forget this point of having to hold everything constant. At this point, you may be wondering what exactly is not a general linear model, as I have hopefully broken down the boundaries of all the methods that you may have learnt in an Introduction to Statistics course. There's quite a lot of things that are not a general linear model, and quite a lot of reasons why things may not be a general linear model. Probably the most commonly considered one in terms of where we go next is thinking about the error term. So if we have these residual errors, the difference between our observed and our predicted value from our model, if we consider that these aren't independent, if we consider that they don't follow a normal distribution, if we consider that they don't have the same level of variation for any given value of x, or any given combination of our x variables, this is where the assumptions underlying a general linear model start to fall down. All of those assumptions can be tested and assessed. Again, there's some nice resources below which will go into that in a little bit more detail. And where we see that those assumptions don't hold, that's where we start to think about converting up to a generalized linear model, or maybe a generalized linear mixed model. And we'll talk a little bit more about that in a later video. Some of the other reasons why a model would not be a general linear model is if we're dealing with what we would call a multivariate analysis, in which case we'd have more than one y variable. We're still having a general linear model however many x variables we have, but if we have more than one response variable that we're interested in predicting from the same model, this then becomes multivariate. If we have a non-additive relationship in how we want to build a curve, we saw with the quadratic and the logarithmic or exponential, we can build that for an additive model. But that's not the case for every possible curve that we might want to draw, and we do need to have an additive equation for this to count as a general linear model. We also might have the situation where we don't consider our parameters, our betas, our coefficients, to be fixed constants that we're trying to estimate. We might think that these parameters themselves have some underlying variability. And if we start to think in those terms, this is when we start to move towards Bayesian methods of considering our parameters themselves to be variable rather than fixed. Those last 3 points are perhaps more conceptual questions about how we build our model. In these cases, we're building something which is fundamentally asking a different question or assessing our data in a different way. Whereas when we're looking at the residual error term, we're looking at perhaps the better way to answer the same question. And that's what I'm going to talk about more in the next video.